All right, please, Chrissy, go ahead.
So, hi everyone, welcome again to your Quantum Matter seminar. Today we have the pleasure to receive Matteo Ippoliti from Stanford. He's a postdoc there, and he's going to talk to us today about this business of fractally entangled states generated by non-unitary dynamics. So Matteo, the stage is all yours, and take the count.
Great. Yeah, thank you so much for the introduction, and thank you for organizing this great seminar series. So today I'll be talking about, as Chris has said, this non-unitary dynamics and generating interesting states with it. This is based on very recent work posted really just a couple of weeks ago with Tibor Rakovsky, who's another postdoc fellow at Stanford, and my advisor, Vedika Khemani. And also on this piece of paper, also with Vedika from earlier this year. So before I begin, I wanted to situate this work in context a little bit. And the setting is that of the frontiers of quantum dynamics, which in some ways are expanding due to the introduction of these new devices known as noisy intermediate scale quantum devices, or NISQ, which are bringing to the table unprecedented capabilities for quantum control and measurement, performing measurements on quantum systems. And these are, interesting from at least two perspectives. One as computers, right? You obviously want to design quantum computers that can perform useful tasks, but also as many-body quantum systems in their own right, just laboratory systems of many interacting qubits. These are very powerful and interesting, and they're opening up new directions in out-of-equilibrium and open system dynamics in particular. And a very important role in these questions is played by the dynamics of quantum entanglement. This underlies many things, from the definition of phase structure out of equilibrium to fundamental questions about the onset of quantum chaos and thermalization in isolated systems, and to both practical and fundamental questions about simulability through either classical computers or quantum computers. And even more fundamentally, possibly the emergence of gravity and even space-time from entanglement itself. So for the talk today, I want to talk about entanglement dynamics in particular, and a very powerful and useful tool that has been used in the past to learn about this is given by random unitary circuits. So these are some of the papers on this. There's many more, obviously. But the idea there is to try to learn about how quantum entanglement behaves in time, and to do so by stripping away as much structure as you can from the regular quantum many-body problem, where typically you have a Hamiltonian that's maybe static or time-dependent, or have any sort of symmetries, conservation laws, and things like that. Here you're trying to take all that away and just look at systems where the only constraints are locality and unitarity, and see what you get. And there's been lots of interesting things that have been learned from that method in the past 5 or so years. And more recently, just really a couple of years ago, this set of works has been expanded by adding to the mix non-unitary processes, specifically quantum measurements. And these are some of the early papers on this. And interestingly, you get new and exciting phases of matter defined by entanglement out of equilibrium that are basically made possible by the introduction of these non-unitary processes. Also now, if you view unitary circuits as a particular corner of this bigger unitary measurement space, you can also look at the opposite corner, where you have only measurements, and just the only thing you're doing is just monitoring the system through measuring different operators. And quite surprisingly, you get a rich and interesting phase structure even in that setting. And finally, all of this lives in the biggest possible space of quantum dynamics that you could have, which would also include quantum channels that represent decoherence, possibly feedback and interactions with classical computers, and so on and so forth. And these are all things that, of course, make sense in theory, but are also becoming experimentally more and more relevant as these devices sort of improve and become more important in the progress of the field. Good. So I want to give you a short introduction about more specifically this unitary measurement space. And here the typical toy setup that one considers is an array of qubits in one dimension. So all these vertical lines, such as qubit word lines that are evolving in time. And they're doing so through a combination of unitary processes that are these gates, these blue boxes, and projective measurements that are these dots. And the key knob that you're tuning here is the rate at which these measurements are being introduced in the system. So p equals to 0 is a case in which there's no measurements at all. And so there you recover unitary dynamics, where we know that absent special constraints on the gates, you obtain at late times a highly entangled thermal state. Conversely, if you
may I ask a question? I mean, very
Sure.
naive maybe, but is there a particular reason why you want to introduce pairwise unitaries and not, more extended ones?
Right. So I guess one answer is because this is the simplest thing. You could, and in some cases, people have looked at more complicated versions of this model. I guess 2 is the minimum number that gives you any interactions. So if you want a local, spatially local thing, this is the minimum toy model. You can also do something called k-local, where you have few body interactions, but they can be sort of arbitrarily far away in space. So that's another thing that's been looked at extensively. But for the purpose of today, we're just going to stick with actually spatially local things and really nearest neighbor gates. That'll be convenient for the following.
Thank you.
Good. Yeah, thank you for the question. And yeah, everyone feel free to unmute and ask questions during the talk. Good. So yeah, I mentioned this first, endpoint, no measurements, everything is unitary. You got a thermal state. That's fine. The opposite endpoint, where you have measurements all the time, so p equals to 1 means that every single one of these bonds is being measured. That basically freezes your quantum state in place. It doesn't have a chance of evolving into anything, and so its entanglement is going to remain, 0 or very limited, basically. And this is something sometimes called the quantum Zinn effect, or a version of it at least. And so the surprising finding from a couple of years ago is that these 2 sort of simple endpoints actually extend to phases in whole intervals in this measurement rate p. And these phases meet at a sharp critical point that really behaves, for all intents and purposes, as a quantum phase transition. So you have this volume law phase. Volume law refers to the scaling of entanglement. The entanglement of a system scales with its volume. But interestingly, despite the fact that this p equals to 0 point is thermal, the rest of this phase, even though it's volume law, it's non-thermal. So it's a qualitatively new kind of volume law entangled phase. Right, so this presents a new kind of entanglement phase transition, which adds to the catalog of known ones, which basically previously involved the many-body localization transition, where what's changing sharply is the entanglement scaling of individual eigenstate of a Hamiltonian or time-dependent, flow K unitary. And also, in some sense, the fault tolerance thresholds in quantum computing. Those are also sharp transitions in the entanglement property of some system that's executing quantum computation. And more broadly, this setup presents a new arena for playing with phase structure out of equilibrium, which has attracted lots of attention in the last couple of years and has seen many extensions in different directions. And also, just as of this morning, I was reading the Condensed Matter Journal Club, and just this morning, Sid Parameshwaran posted a very nice short review of some of these papers, which I encourage you to look up if you're interested. So then, this is all very interesting in theory, but how about experiments? What are the practical considerations that come into play with measurements? So the first thing to bear in mind is that in order to measure anything, you don't just need one wave function, but you need many copies of it. That's because, let's say you want to measure, say, the z component of spin. That's some real number, 0.345. But the only thing you're getting from your measurement is either spin up or spin down, so plus or minus a half. And so you're going to have to average over many, many iterations of this measurement in order to obtain, whatever real number you're targeting. So this requires them producing many, near identical copies of the state, which can always be a little hard due to engineering problems like quantum control, decoherence, etc. But those are practical matters that one can improve with technology. What's a little more concerning in the presence of measurements is that there is more of a fundamental, seemingly there is a fundamental obstruction here. And that's because the outcomes of quantum measurements are intrinsically random, as far as we know, right? Unless the laws of quantum mechanics are revised in the future, they're fundamentally random. And so even if you're a perfect quantum engineer and your quantum gates are exactly perfect, error-free, identically repeated from run to run, your measurements are going to be to spit out some random sequence of outcomes. And so in this toy example here, I have some array of gates and measurements in space-time. And these three measurements are giving me some string of outcomes, for example, spin up, spin down, spin down. And if I attempt to repeat it, maybe for some time I'm lucky and I get the same outcome, but eventually I'm bound to get a different one just by sheer chance. And once that happens, you are in a bit of trouble. Because if you simply ignore it and just do your quantum shot measurements anyway and average over outcomes, you actually get a completely featureless density matrix. So all of this interesting physics of the entanglement transition is washed out and you don't see it. You really need to be able to follow individual quantum trajectories in this evolution. So quantum trajectories means a particular sequence of measurement outcomes that produces a particular wave function. So naively, what you can do there is a thing called post-selection. So if you obtain the first sequence of outcomes, you then decide, okay, I'm going to only use wave functions that are produced with that same sequence of outcomes. That's fine, you can do that, and it's going to work, but it comes with an extremely costly overhead. Basically, because measurements are random, each one of them comes with some probability of being wrong, and so it just exponentiates over the number of measurements you have. And so if you have a density P of measurements in space-time, this overhead is exponential both in the product of system size and circuit depth, which is just a terrible scaling if you're thinking of taking a thermodynamic limit. So there are some ways around this problem. One is to not even try to prepare the state and just try to learn about the phases and the transitions just from the entropy of the measurement record, which you can do. Another way is to try to prepare the state by doing some sort of decoding where any wrong outcome you get can, in some cases, be corrected to the one you wanted if you have, say, a classical computer that's running a simulation in parallel that tells you what to do. This is a closely, this problem is closely related to quantum error correction, and in some cases, it's computationally doable. But in general, it can be hard. So third approach is to simply accept that this overhead is there and just try to minimize the number of measurements that are happening just overall and use some trick to sort of obtain effective non-unitary dynamics with fewer or no measurements, which is the approach we're going to take in this talk. Okay, so this is to the introduction, and here's the outline for what I hope to cover today. The first part is exactly this kind of trick I was just mentioning, which for us is going to be space-time duality. So this is an experimentally motivated way to make interesting non-unitary circuits, which I'll explain in the following. And then for the rest of the talk, I'll discuss what we can do with this. So here I'm going to discuss this recent paper where we use this idea to make interesting entangled states. And then if we have time at the end, I'll discuss how we can use this idea to bring some of this physics to the lab by essentially eliminating this post-selection overhead. Okay, so the idea of space-time duality, in very simple terms, is to exchange the roles of space and time, which at the most basic level, so the most elementary building block of our quantum circuits, is just a 2-qubit gate, which has 2 input qubits that are coming in at the bottom, 2 output qubits that are going out at the top, and has some error of time that's denoting which way time is flowing and which way the gate is unitary, which I'm going to also sort of keep a little marker with this arrowhead that is going to remind you which way the gate is unitary. So the idea then is just to exchange the roles of space and time and view the same object sideways, which according to this fictitious error of time t-twiddle, in such a way that the input states are actually I1 and O1, and the output states are I2 and O2 that are on the right. And this matrix is obtained, which is just a reshuffling of the entries of the matrix U that you had, ends up being non-unitary in general. So to give you an example, if you take the identity matrix, which has this matrix representation, as we'll know, and you can also picture diagrammatically as the 2 qubits coming in and not talking to each other and then going out. If you flip it on its side, the particular reshuffling of entries you get is this one, which gives you a projector onto this particular state, which is up, up, plus, down, down. And diagrammatically, you have the two qubits are coming in. They're being projected onto this Bell state. This is what this downward arc represents, projection. And then they're being sort of reinitialized into that same Bell state, which is now this upward arc. So these Bell states are going to come back throughout the talk, so it's sort of useful to remember them. But then another point about this that's worth making is that the effective measurement you get is completely deterministic. That's because U twiddle is every bit as deterministic as U, so there's no intrinsic randomness in it. And so that's kind of the motivating idea we had. Can we use this deterministic sort of pseudo measurement object to reproduce the effect of measurements without the randomness? And this is not obvious, right? This is all on paper for now, so we're going to have to go through it in practice and see how that works out. But before I do that, I also wanted to point to some other works that have used similar ideas very recently for a variety of questions in quantum dynamics, ranging from chaos to the emergence of local thermalization in closed systems to even many-body localization. In all these cases, you can view quantum circuits sideways, and you can use that to learn sort of useful and interesting things about the unitary circuit that you started from. So our point of view is a bit different in that we actually we don't want to learn things about the unitary circuit. We want to genuinely engineer some non-unitary process by doing this thing sideways. But these are all very related ideas. And I also mentioned that there is a very interesting class of models where this duality transformation, where you exchange space and time, actually leaves the circuit, preserves unitarity, which is a very special constraint. It's genetically not true, but in some of these, in these models, it's true. And that comes with some very strong constraints that afford you a great level of analytical control and have enabled some important results in quantum chaos. Okay, so that brings me to more practical considerations of how do we do this in the lab. And the idea is to, instead of trying to flip, gate by gate, let's try to build up our circuit like Legos. We stack these gates on top of each other in this way. And then we try to traverse this circuit we got sideways, just as a whole. So again, as a reminder, we have laboratory time, which is a physical unitary time, which is flowing vertically, bottom to top. And it's also sort of, as a reminder, these little arrows in the gates are the direction of unitarity. And then we have this dual or non-unitary time that's flowing left to right. That's this arrow here. And that's what we're trying to target, we're trying to realize effectively through this process. So if we were able to realize this diagram, where we have an input state coming in the left and an output state coming out the right, then these two states are actually related by precisely this dual quantum circuit that we're trying to realize. Okay, so there are a couple of conceptual issues in trying to realize this. The first one is that we have this, in order to implement open boundary conditions on this sideways circuit, which will be this bottom wall and this top wall, you have to fix both the initial state and the final state in the laboratory, which is a bit tricky. So how does that work? Well, now it's useful to remember what we did just earlier when we looked at the spacetime-dual identity, which gave us those two arcs, like a projector and a new Bell state. And these are exactly the things we get here. So at the bottom, we have, that means that in the lab, we're supposed to prepare these Bell pairs, up, up, plus, down, down. And then at the end point of our dynamics, we're supposed to projectively measure onto those same states. And these are precisely the costly, post-selected measurements that I was telling you about. So these will come with an overhead that we'll quantify later, but suffice to say, we can do it. It's a physical thing that can be done. And then the second issue is that both the input and the output states exist on time-like surfaces. So this is very unusual, right? If you look at the input, for example, it exists on some one qubit in the lab, so one position, but at different times. So we want to make sense of that and convert it into something operational. So that can be done, for the input state. The most convenient thing you can do is just to pick this particular tensor product of nearest neighbor Bell pairs, which again are these little arcs here. And that's the easiest thing because it's simply sort of automatically natively implemented by just having open boundary conditions on that edge in the lab, right? This just means that this qubit is partaking in interactions with its neighbor to the right, and then is not doing anything because it doesn't have a left neighbor on these time steps, and so just sitting there, and then again interacting with the right neighbor, and so on and so forth. So that takes care of that. What's a little more, what's a little trickier is that the output state now lives on this dangling legs, which I've put little color dots on it to as a guide to the eye, and we would like to turn it into more of a conventional state that exists in space that then an experimentalist could just do whatever measurements on. And this we can do at the expense of introducing some ancillary qubits, which are also coming in these up plus down bell pair states next to our system, and then acting on them with swap gates. So swap gates are just these crosses when two legs are going over each other. That's a swap gate. And it only interchanges the position of the qubits without doing anything to their states. And so if you do this, what ends up happening, and you can convince yourself by tracking some of these dots from start to finish, is only that you take this one state you had and you exactly reflect it from this vertical surface to this horizontal surface. That's all you're doing. And this is inspired, it's sort of a dressed up version of quantum teleportation, which is a textbook protocol that exists. And here it's complicated by the fact that you're trying to teleport a whole big state and not just a single qubit. So in the end, this concludes the protocol, because we're done. We've got our output state that we wanted, and we got it at the expense of doing only unitary gates, which is fine. We have them in our toolkit. A small number of ancillary qubits, which is also fine, and some order L quantum measurements. So that's the costly part, but it's important to emphasize that this is order L as opposed to order L times T. So it doesn't scale with the depth of the circuit, which is a much more much lighter overhead than the case in which you're doing measurements everywhere inside your bulk space-time of the circuit. Okay, so I hope I've convinced you that this stuff is something you can do in principle in the lab with resources that are quantifiable. So it's not science fiction. We can actually, we can think about this as a physically motivated setup, and we can use this to make interesting things. So this is going to be the bulk of the talk. How can you use this idea to make interesting states that exhibit novel forms of entanglement? Again, based on this recent archive preprint. So our goal here is to, using this setup whose physical meaning I just described, can we study the quantum entanglement of a state that you produce at this output, which is this time-like wall of your circuit? Can you quantify its entanglement, in particular in the limit of late dual time? So you take this T2 to be very big, you obtain some steady state, and you want to characterize the scaling of its entanglement as a function of subsystem size. And just as a reference point, you can compare this to the more canonical, entanglement calculation in unitary circuits, which looks like this, where your final state is at the end of time, not at the end of space. And even though in the bulk these two are the same thing, this change in boundary conditions really is quite, it has quite drastic effects, and it's really not a trivial thing to know beforehand whether the two results are going to be related or how, in what way. So that's the problem statement. And because the state we got here is pure, the entropy of subsystem A really is equal to the amount of information that's shared between A and its complement A bar, because there's no third party, there's no environment that could also have that information. It's really all between A and A bar. So that's what we're going to quantify. And a great simplification that occurs if you take A bar to be infinitely big. So if you take your finite subsystem to be embedded in a semi-infinite chain, then in that case, all the information that crosses this cut B, that's separating the two subsystems, ends up exactly in A bar. So formally, we have a result. We can prove there is an isometry between the qubit states that go through B and the state that ends up in A bar. But morally, what's happening is that any information that crosses cut B finds itself basically on a one-way street where unitarity is forcing it to go one way only, up. And that is until it hits this, this ceiling where it could get a chance of turning back around and going backwards in time. But if you push the ceiling to infinity, that never happens. It doesn't have a chance to do that. And so it gradually leaks out through a bar, and all of it ends up in a bar. So that's kind of the qualitative hand-wavy explanation, but there is a rigorous statement we can make. So with that in mind, we can then drastically simplify this problem, where instead of having this whole big tensor network, we can discard all, the entire segment that's above B, and we're left with this sub problem, right? And we're trying to quantify the information that's shared between A and B. And again, A is this time-like surface, B is now a space-like surface, and this looks like a very weird state, but it's a totally fine tensor network as a matter of math. And as we'll see in the following, it also gains a nice physical or dynamical interpretation at the end of this. So the state as a whole is pure. So again, we're trying to calculate the entropy of A, and we can do so by tracing out either subsystem, A or B. So it's convenient to trace out A in particular. So you have this wave function on AB. As always, you try to form the reduced density matrix on B by taking a bra and a ket and tracing them out on a subsystem, which diagrammatically looks like this. So the bra would be the top layer. I guess the ket would be the top layer, which is yellow gates, and the associated bra would be the bottom layer, which are the shaded ones on the back. And then you're tracing them out by matching the legs that are sticking out on subsystem A. Okay, so this is a diagram, but now you can interpret it in real or laboratory time as a particular dynamical process, which is the following. So in the bulk of your system, there are unitary gates that are acting and evolving your qubits. That's fine, as usual. But here at the edge, this particular configuration of contraction of legs can be interpreted as the action of a quantum channel, which is the fully depolarizing, or also known as erasure quantum channel, which does the following. So it takes the input state, it traces it out on that qubit, single qubit state gets traced out and gets replaced by the identity. This is what's happening at every one of these gaps in between the states of that one qubit. And so what's happening here is that you're injecting entropy through the edge by doing this decohering process. And then the unitary part of the circuit is spreading that entropy into the bulk. And you're going to obtain some mixed state at B, whose entropy is what you're after, basically. So with this in mind, we get to this key result, which is connecting the entropy of the states produced by non-unitary dynamics to the entropy of these states produced by unitary dynamics with edge decoherence. So in particular, so there are two effects from space-time duality here. One of them maybe is the more expected one, and it's that you're exchanging the roles of size and depth. So space and time, the spatial and temporal extent of your circuit are being exchanged. So on the left-hand side, you have depth t twiddle and subsystem size L twiddle. On the right-hand side, you have the opposite. This is maybe expected. The less expected thing is that now you have this twist of edge decoherence on one side of the duality, which you don't have on the other. So this is the key result. And it simplifies further if you take the limit of t twiddle going to infinity. So you take this slab and send one edge off to infinity. And in that case, we get that the steady state, spatial scaling of steady state entanglement in these non-unitary circuits equals the amount of entropy that you can inject into a semi-infinite chain by decohering its edge as a function of time. That's the right-hand side. So this is, I guess, can be a bit confusing, but it's, we have, it's going to be proven rigorously, and it also, leads to this appealing physical interpretation that also enables quite powerful numerical simulations that I'll show in the following. And also, if you don't like mixed states and decoherence, you can also just do without that. And you can purify this quantum channel that's acting at the edge by using essentially the same trick with ancillas and swap gates. And this maps onto a completely unitary evolution with a very special entanglement cut. So it's a cut between two subsystems. One of them has whatever gates you chose to implement. The other one has only swap gates. And to compare it to the more normal entanglement cut that you have in the usual setting, these look very similar, except of course, the nature of the gates that are present in subsystem A here. And the physical difference is that in a normal case, just this one, information is free to propagate past the cut and then maybe come back, just due to the particular nature of the gates that act on it. It can get reflected and come back. In this case, instead, as soon as the information crosses the cut, it gets basically radiated off to infinity and never has a chance to come back. So this leads to specific differences in the behavior of entanglement, as we'll see in the following.
Question.
Yep.
I don't know if I missed something, but it looks to me, at least from inspection, that this statement that you made, this correspondence, doesn't really depend on the boundary conditions or on the initial state on the left, right?
Yeah. So that's a bit subtle. I sort of swept around the rug a bit. This works out in a sort of easily provable way if you have this this boundary state on the left. If you have a more, maybe a single site product state, then naively the proof sort of needs tweaking. So we think that the scaling is the same, but there might be like prefactors or it's not an exact identity at that point. You have to modify it a little bit. Yeah, I can get into more detail later if you want.
Okay, thank you.
Yep. Okay, so that was the heavy part, I guess, all the theoretical toolkit we built, and now we just want to use it onto a class of models we know that exhibits rich variety in its growth of entanglement. So here, for example, with this kick-dicing model, which is a time-dependent Hamiltonian that alternates between Z part and a transverse field part, as you tune these different couplings, you can generate this whole range of behaviors that go from Anderson localization, where entanglement essentially doesn't grow past a constant, through many body localization, where it grows logarithmically in time, so very slowly. And then you can cross into a thermal phase, where at first entanglement grows algebraically as a power between 0 and 1. And then eventually it becomes fully chaotic and grows ballistically with some finite velocity. And eventually there are these special dual unitary points that I briefly mentioned earlier, where not only you have ballistic growth, but the velocity is also fixed to 1, it's maximal. And these are realizable within this class of models. Just we're not going to use this specifically, but just to ground it in reality, you can actually do all of these by tuning some parameters in a particular model. And the idea is to use this variety in the temporal growth of entanglement in unitary dynamics to generate a similar variety of spatial scalings of entanglement in non-unitary circuits. So that's what we do in the paper. And the results are summarized here, where sort of to 0th order, it looks like a 1-to-1 correspondence, like we have log t goes to log L and t goes to L and so on. And remarkably, this fractional subballistic scaling with time becomes fractional power law scaling with space, which is something that you don't commonly have in unitary dynamics. So it's a novel family of so-called fractally-entangled steady states. And then other comments in order, we don't get, or it's impossible to get area law entangled states absent some fine tuning. So even the Anderson case becomes, develops divergent entanglement. And finally, these log corrections also pop up sort of across the board, pretty much. We also get them in chaotic circuits, and they come from edge decoherence through the mapping that I just discussed. So I'll go through some of these examples. So starting from Anderson localization, where if you have a circuit that has a free fermion representation and has disorder, you obtain these Flohe-Anderson orbitals, which are just exponentially localized about some site in the chain with some finite localization length psi. And in unitary dynamics, these orbitals, their existence means that your entanglement doesn't grow past a constant, just because the orbital empty or occupied orbitals do not dephase, and so they never develop any entanglement past some constant that's given by their tails sort of straddling the cut, but giving you some finite contribution. So the question here is, what is the effect of edge decoherence? Because that's the relevant variable in our duality mapping. And here, what we find, this is a cartoon of, you have all your Anderson orbitals, and you're sort of you're perturbing them at the edge with this decoherence process. And the question is, what happens? So even if you are localized very far from the edge, you have this exponential tail, which is going to have some non-zero weight at the decohering site. Exponentially small, but absent fine-tuning, non-zero. So there is some associated timescale that's blows up exponentially with distance, but it's still finite for the decoherence of any one Anderson orbital. So over that timescale, the content empty or occupied of the orbital gets completely dephased, and that contributes 1 bit to the mixed state entropy. So these are the results of numerical simulations, which show you sort of for single realizations, you can really beautifully see the decoherence of these individual orbitals that are all of these plateaus at integer values, number of bits, and sort of going up in steps. And on average, that gives you this logarithmic divergence of the entanglement entropy. So again, basically, we calculate this in time as a unitary evolution with edge decoherence, but then due to that duality, this equals the spatial scaling of the steady state entanglement in the sideways circuit. And then, interestingly, the same picture survives in MBL, so we can turn on weak interactions, and the system can remain localized, except now, instead of Anderson orbitals, you have so-called local integrals of motion, or LBITs. And these are very similar objects, except they also interact, so they dephase one another with some JZZ type interaction. Sorry. Right, and so we get a similar logarithmic divergence in that case. Then as you crank up the strength of interactions, eventually you transition into a thermal phase where you don't immediately end up with a ballistic growth of entanglement. That only happens somewhat later when your system gets less disordered. Initially, you have this so-called Griffiths regime, in which you have basically you're close to the transition on the thermal side, and you have big patches of your system that would like to be localized, essentially, very close to localized, except they can't because they're surrounded by thermal environment. But nonetheless, they can really slow down thermalization and entanglement spreading by a lot. And so sort of an analysis of various length and time scales leads to this fractional power law in time for this thermal phase near the transition. So this is a very tough problem to analyze macroscopically because of the large length and time scales involved, but there are powerful coarse-grained models you can look at. So in particular, this one that was put forward by Adam Nahum and collaborators in 2018 consists of a one-dimensional quantum circuit, which is great because that's precisely the setup that we know how to study with our mapping. And the idea is that it's a coarse-grained attempt, it's an attempt at coarse-graining features of big subsystems. So if you have a big patch of your system that's propagating entanglement at some rate, then you convert that into a particular bond in this chain that only sees a unitary gate every with that particular rate. So practically for each bond, you sample some rate between 0 and 1 from some distribution, and then that rate sets how many gates are being dropped on that particular bond going forward in time. So this generates bottlenecks that are locations where the rate is very, very small. And that means that for the most part, those bonds are inactive, and only every now and then they're getting some chance of coupling the subsystems on the left and on the right. So I'm showing a sketch here with two bottlenecks where there's very few gates, right? And by tuning this parameter, you can control how what is the distribution of these bottlenecks, how likely they are, and you end up getting an analytically provable scaling of entanglement with some exponent that's exactly tunable between 0 and 1 in this way as a function of this parameter A from here. So now the idea is to view the same model sideways. So again, same diagram, but now the arrow of time is going left to right. And the meaning of bottlenecks changes quite sharply, because now they aren't bottlenecks in space, but rather they're bottlenecks in time. So a bottleneck time step is a time step in which, if you look at what's happening here, almost all of your bonds are being projectively measured. So if you're traversing this particular rectangle, horizontally, well, then there are two qubits that are evolving, with some combination of unitary and measurement, whatever. But then all the others are being exactly projected, and so all of their entanglement is being, destroyed or moved elsewhere. So these bottlenecks are basically like catastrophic events where most of the entanglement is destroyed, and only a very sparse network of entangled sites is left behind. So this is kind of the mental picture for that. But numerically, we can just do this with stabilizer numerical simulations on some particular class of gates called Clifford gates that enable us to do efficient simulations and do thousands of qubits. And as we tune this parameter A, which again controls the distribution of bottlenecks, we get the entire fan of power laws basically between 0 and 1. It's very nice. The dashed lines are meant to be the prediction, the analytical prediction. They don't match exactly, but we have some understanding of the corrections to scaling, and we think that the data should asymptote to the correct prediction. So that is verified numerically. And also, in terms of what these fractional power laws mean, it's not just the mean of the entropy, because obviously we have randomness in the setup and we need to average over it. But it's not just the mean of the entropy that's exhibiting this very unusual power law scaling, but its entire distribution obeys the scaling collapse as a function of subsystem size. So if you rescale it by a suitable power law subsystem size, the entire distribution collapses. And that means that not just the mean, but all the moments are statistically self-similar over all length scales. So yeah, this is a very unusual behavior that's intermediate between logarithmic and volume law, and it's generically not seen in many body unitary dynamics. There are some exceptions that are either free or sort of very special Hamiltonians with some algebraic properties, but in sort of generic many body dynamics, this is not seen. So it's a very sort of a remarkable consequence of expanding the space of models with these non-unitary elements. Okay, so now if we push further and we get to chaotic dynamics, we have again, it's helpful to use toy models, and here the very canonical toy model is using Haar random circuits, which means circuits where each gate is sampled independently and identically from the unitarity invariant or Haar measure on the unitary group. And here Q is the on-site table space dimension, so it's 2 for qubits. You can let it be a variable. And there are analytical techniques for computing the average of the purity, which is this trace of rho squared that's associated to the entropy, this annealed average of the entropy. So I won't go through details, but basically trace of rho squared comes with 2 copies of the bra, 2 copies of the cat. So it's 4 layers, which are sketched here. And you can do this average analytically, and you get some effective StatMech model that can be treated exactly. So in particular, there is a very appealing mapping to a random walk problem where your choice of entanglement cut determines a random domain wall, and then the location of the domain wall can hop left or right every time a gate acts on it. And so just carrying this through gets you this analytical result where the entanglement growth is ballistic, and with an entanglement velocity that's exactly computable. So this is for unitary circuits. This is an older calculation. And then we just adapted it to our particular problem with these boundary conditions that have edge decoherence here. And there is a very appealing picture here because the random walk looks exactly the same as long as you're in the bulk. But if you're trying to sort of walk past that edge on the right, you're being pushed back with a penalty. So you're losing total probability. Turns out that there is a function of Q that's less than a half. So the total probability for these processes is less than 1. So your random walker has some chance of getting killed at every unit of time. And if you go through the calculation here, this survival probability gets you this universal square root of t correction, which is typical for random walk problems. And once you convert this purity to an entropy, this gives you this universal 1/2 log L subleading correction. And so 2 comments in order here. First, we got an entropy density, which equals an entanglement velocity. So again, this is sort of intuitively expected from spacetime duality because we got, we mapped an entropy per unit length to an entropy per unit time. So that's kind of a consequence of spacetime duality. And then this logarithmic term, which seems, it's small, so who cares? It's important because it signals that this is really a genuinely non-thermal volume law entangled state. And these states have been studied in also, they also show up in the more general unitary measurement problem. And they also have logarithmic corrections, and it's conjectured to be universally 3/2 the coefficient. And here, turns out that this is actually something we realized after posting, but the problem we tackled was this one of finite system at the edge with a semi-infinite complement. So kind of like this, there is a wall and then there is an infinite complement. And here you get this random walk survival probability, which goes as square root of t. But if you did a subsystem that's in the bulk of an infinite system, infinite on both sides, then you will get actually 3/2. So that's the apples to apples comparison. And so based on that, we conjecture that this particular duals of chaotic models actually live in the same non-thermal volume law phase as the unitary measurement circuits. So this is not confirmed yet. They could just have the same coefficient and other properties may be different, but at this moment, it seems plausible that they're in the same phase. Good. So that's all I wanted to say about that part. And then in the last 10 minutes, I just wanted to quickly flash what we can do more on the experimental front with exactly 0 post-selection, which goes back to this paper from earlier this year. So what we can do with absolutely no post-selection is a slightly different problem. So we have to be a little flexible. But this goes back to some papers by Gallants and Hughes about the dynamical purification of mixed states. So this is in some ways a twin problem to the entanglement dynamics problem that we've been studying up until now, and consists in sending a mixed input state, so rho proportional to the density, through some non-unitary machinery. And because the U twiddle is not unitary, the output state, which is U dagger rho U, ends up being not necessarily the identity, precisely because the evolution operator is not unitary. But the question is, do you get a pure state, so something like a projector on a single state, or do you still retain some finite entropy density? Do you still have a strongly mixed state in the output? And it turns out that the answer to the question leads to a sharp phase structure for these dynamics. So there is a pure phase where the answer is that yes, you quickly converge to a pure state, and there is a mixed phase where instead you maintain finite entropy density for very long times. And these two phases mirror almost one-to-one with the volume law and area law phases in the pure state entanglement dynamics in the presence of monitoring. So they're very, very closely related problems. Good. So our target is to measure this entropy density of the final state by taking advantage of spacetime duality. So again, here I've shown, so in principle, this could be any non-unitary object you want, but we're taking them to be spacetime duals of unitary gates. So the little arrow of unitarity here is flowing sideways.
Sorry, naive question. You're not applying e to the minus beta h, right? So you're applying something else.
That's right. Yeah. So, but that's closely related as well. So that's an interesting point. Here, if you could do something that's through this non-unitary process, you could do something that's like e to the minus beta h1 followed by e to the minus beta h2, like a trotterized imaginary time evolution. That's in principle something you could do.
But in that case, if you're trotterizing a Hamiltonian, won't you end up in the ground state of the Hamiltonian?
Yeah, so good question. There is a subtlety with, you can't actually trotterize it very finely because like a very small throttle step means that you're very close to the identity, and you can't be very close to the identity in these dual gates. Like you have to be far enough for you can prove this. So a very coarse throttlization of a Hamiltonian, which doesn't necessarily end up in a or maybe it ends up in a ground state, but something very non-local, like something very weird.
All right.
Yeah. I also have a question. When you talk about the entropy density at late times, what are the typical time scales for you to consider that you are late in time or no?
Oh yeah, that's also a great question. So key point here is that everything eventually hits a pure state if you just run for long enough. But the mixed phase, the mixed phase takes exponentially long in system size, whereas the pure phase takes order 1 or at most logarithmic. So when I say long times, I mean like polynomially long in system size. So, like 10 times the system size is late or something like that. Good. So this is the setting of the problem that we're trying to address. And the thing to calculate is this ideally the entropy, but the easiest thing to calculate is the purity. So trace of rho squared, which you can obtain by in some ways interfering 2 copies of this output state, which you can do like this. So 1 copy here, 1 copy there, and you're contracting all the legs. And then by taking advantage of space-time duality, we show that you can measure this quantity, this entropic function, as a correlator in a unitary evolution without any post-selection on measurement outcomes. And we detail an experimental protocol that gets this quantity, this entropy density, on basically a present-day digital quantum simulator, so with conventional technical capabilities. So the idea is, I won't go through it in much detail, but I'll just flash some animation to convey the message. So we rotate the diagram of interest and we recast it into something that we can interpret as being some combination of unitary gates on some specified initial state and Bell measurements that I've specified here. But the key point is that these Bell measurements are not post-selected. You don't want them to have one outcome necessarily. You use the entire statistics of measurement outcomes. So so then this is detailed in more specifically here. It's not super important exactly how you do it, but it's like a little flow chart of do these operations, perform this measurement, conditional on the outcome, do this or do that, and at the end of the day you record some success or failure, so like a 0 or a 1 for that given run of the protocol. And at the end of the day, the ratio of successful runs to total runs gives you exactly, so with no prefactors or anything, exactly gives you this trace of rho squared, which is a nice sort of easy to implement protocol. And this purity is related to the entropy in this way. And if you imagine that this success probability is decaying exponentially as a function of the number of measurements you have here, which is, again, that's sort of intuitively following from every measurement may or may not give you what you want. And so as you do more and more of them, you expect some exponential decay. Well, this exponential decay converts into an entropy that scales extensively with the size of your virtual subsystem. And so you can extract the entropy density from this inverse time scale. So if you can get this exponential decay, do a fit for the time constant, that's the order parameter you're after. Okay, so this brings me to my conclusion. I hope within a reasonable time frame. So I've introduced space-time duality as a physically motivated route to make interesting non-unitary circuits. With this, we have engineered sort of a zoo of interesting out-of-equilibrium states that have really all kinds of entanglement scaling, including ones that we know from unitary dynamics and ones that, like fractal entanglement that generically appear to be impossible. And then what I just discussed now is the possibility of implementing this measurement-induced purification dynamics without any randomness and therefore without issues of post-selection. And so zooming out a little bit, these works fall into this context of pushing this non-unitary frontier of quantum dynamics, which is only just beginning, and people have already used this to propose new possibilities for entanglement dynamics and phase structure out of equilibrium. And so obviously the big question going forward is what else can we do with this? And what are other interesting theoretical directions that lie at the intersection of interesting and sort of experimentally plausible or realistic. So with this, I just wanted to thank the organizers again, thank the audience. Of course, thanks my co-authors, Tibor and Vedika. And again, these are the references. And I also encourage you to check out this other simultaneous paper by Tyrone Grover's group that came out same day as our latest paper that has some complementary results. And yeah, if there are any questions, I'm happy to take them.
Thank you very much for this nice talk. If you want another question, another person in the audience has some question.
Yeah, actually, I have a quick question. So if I remember correctly, in your first PRL paper, I remember you studied a non-unitary, a particular model for the non-unitary circuit whose dual is like a particular Clifford circuit, where you find that the generic outcome is actually a mixed phase, right? And then in the set of new examples you're showing, you're also, it seems like also an areal phase is kind of missing. So is that sort of a generic feature of non-unitary circuit that has a unitary dual?
Yes. So as far as we know, yes. The answer is yes. So you can have areal states that are highly fine-tuned in the following sense. Let me go back to the decoherence picture. Yeah. So if you have, this type of diagram and some bond in your system is completely disconnected, for example, so there are no gates here. Some bond just decouples the left and right. Then, of course, the decoherence only spreads to some finite interval, gets you some, order 1 amount of entropy at late times, and that's it. So that's an areal state. But absent that, so if you perturb infinitesimally any sort of fine-tuned example you can make of this kind, then you generically flow to more than an areal amount, like so a divergent amount. So at the very least, we found this logarithmic amount. Interesting, would be interesting to understand if you can have something lower. But so that earlier phase diagram we had was a particular instance of this phenomenon, which we didn't fully understand back then. I mean, we observed it, but we didn't have this proof yet. And so it would be interesting to develop a sense in which maybe this volume law phase is kind of symmetry protected by the unitarity in the sideways direction. But that's that's kind of where we are now. We don't have an answer to that beyond this. But very good question.
I see. Yeah. So basically, I'm just wondering because I mean the special thing about this class of non-unitary circuit is first, well, there's no randomness, right? It's a, and then second, it has a unitary dual. So which factor is actually more crucial that leads to this kind of phenomena? That's basically my question.
Yeah, I think it's the unitary dual, because the randomness. So first of all, you do have randomness in the choice of gates. So the outcomes of measurements are fixed, but you could sort of get around that. And then for Clifford models, it doesn't matter, right? The outcome is just a phase bit that doesn't affect the entanglement. So so my view is that it's really about the unitarity of the dual. That's kind of in some ways, if you have dual unitary circuits, the unitarity of the dual also has some drastic consequences on all the properties. So maybe this is kind of in the same vein.
Yeah, I think so too, because I think if you simulate the sort of the more conventional like hybrid circuit, right? Even if you say, oh, you only retain sort of the randomness in the position where you make the measurement, but then you fix the measurement outcome, I don't think it's going to change any results. So maybe that doesn't matter so much, right?
Yeah, I agree with that.
Thanks.
Okay, yeah, thank you. A good question.
Any other question? Well, if not, let's thank Matteo again. Thank you very much for accepting.
Great, yeah.
invitation.
Thank you all so
hope-
much.
Bye.